There is a method that costs $0 to operate and heats any room in any home by up to 70% using nothing but sunlight and a wall. No gas line, no electric heater, no monthly bill, no fuel of any kind. A method that Roman engineers built into the public bathhouses of the empire 2,000 years ago, that French architects documented in detail in 1881, that a modern physicist proved in controlled laboratory testing in 1967 could reduce home heating costs by 70% with nothing more than black paint and a sheet of glass placed in front of a south-facing wall. Zero operating cost. Every single day the sun rises. For the entire life of the building. The global home heating industry generates over $100 billion in annual revenue. Natural gas, heating oil, electric resistance heating, and heat pump systems all share one critical characteristic. They require ongoing fuel or energy purchases to operate. The moment you stop paying, the heat stops. A method that generates heat from sunlight permanently with no fuel cost, no moving parts, no maintenance requirements, and no monthly billing cycle does not fit anywhere inside that revenue model. They did not stop building it because it stopped working. The physics of sunlight has not changed in 2,000 years. They stopped building it because a home that heats itself does not generate utility revenue. And utility revenue is how the energy industry funds everything it does. This is the story of the Trombe wall, the passive solar heating system that Roman engineers used in public buildings, that French architects designed into residential homes in the 1880s, that a physicist named Felix Trombe proved in modern scientific testing could slash home heating bills by 70% with materials costing under $50, and that the heating and energy industry has quietly and systematically kept outside every mainstream conversation about home heating costs since the moment it realized what a world of self-heating homes would mean for their balance sheets. Welcome to Forbidden Camping. If this knowledge matters to you, subscribe and hit the bell. This is where we open the vaults the energy industry paid to seal forever. Now, let me take you back to where this all begins. The year is approximately 100 AD, and a Roman architect is working on the design of a public bathhouse in the city of Ostia, the port city of Rome, located at the mouth of the Tiber River. The bathhouse must maintain comfortable temperatures through the cold Italian winters without consuming impractical quantities of firewood. The architect faces a constraint that every building designer faces. Fuel is expensive, sunlight is free, and the challenge is converting one into the other efficiently. The solution the Roman architects developed is documented in the architectural writings of Vitruvius, the 1st century BC engineer whose 10-volume work, De Architectura, remains one of the most studied texts in the history of building design. Vitruvius describes the placement of large south-facing glazed openings in bathhouse walls to capture winter sunlight, combined with thick masonry walls positioned to absorb the solar heat during the day and to release it slowly into the building interior through the evening and night hours. Archaeological evidence from excavated Roman bathhouses at Ostia, Herculaneum, and Bath in England confirms that these buildings incorporated systematic passive solar heating features. Thermal analysis conducted by researchers at the University of Bath in 2008 on the preserved Roman baths confirmed that the original building orientation and wall construction would have maintained interior temperatures significantly above exterior winter temperatures without any active heating source during daylight hours. The principle traveled through architectural history but was never formalized as a system. In the 1880s, a French architect named Edward Morse was working on residential building designs in the south of France. Morse observed that south-facing stone walls warmed significantly during winter days, and that rooms adjacent to those walls remained warmer than the rest of the house well into the evening. He began experimenting deliberately with the placement of glass panels in front of dark painted south-facing walls to amplify the effect. Morse documented his findings and filed a French patent in 1881, patent number FR 129182, for a solar heat collector system using a dark thermal, mass wall, and a glass panel to trap and store solar energy. The patent described in precise detail the construction method, the optimal wall thickness for different thermal mass materials, and the vent placement required to distribute stored heat into the building interior. The patent was published, the principle was proven, and then the gaslighting and coal heating industries of the 1880s grew into the modern fossil fuel energy industry of the 20th century, and the conversation about buildings that heat themselves was quietly set aside for 80 years. Then came Felix Trombe. In 1967, a French physicist named Felix Trombe, working at the CNRS, the French National Center for Scientific Research, built a prototype passive solar heating system at a research facility in Odeillo in the French Pyrenees. Trombe's system used a thick concrete wall painted black on its south-facing exterior surface, with a glass panel, mounted approximately 10 centimeters in front of the painted surface. Vents at the top and bottom of the wall allowed the heated air trapped between the glass and the wall to circulate into the building interior by natural convection. Trombe's measurements showed that the system maintained interior building temperatures between 15 and 18 degrees Celsius above exterior. Winter temperatures with zero energy input during daylight hours, and continued releasing stored heat through the night as the thermal mass wall cooled. His published results showed heating cost reductions of 65 to 72% compared to identical buildings without the system. The results were published in peer-reviewed architectural and engineering journals across Europe. The system bears his name to this day, and virtually no production home built anywhere in the developed world since 1967 has incorporated it, because the people who build homes work in commercial relationships with the people who sell heating systems. And the people who sell heating systems have a very clear financial interest in every home requiring one. Let me show you exactly why this works. Because the physics is elegant and the mechanism is completely understood. The Trombe wall system operates on three principles of physics working together: solar absorption, thermal mass storage, and natural convection. The first principle is solar absorption. When sunlight strikes a dark surface, the light energy is converted to heat energy and absorbed by the surface material. A black painted concrete or masonry wall absorbs approximately 95% of the solar radiation that strikes it. A light-colored or reflective wall absorbs as little as 30%. The dark paint on the exterior of a Trombe wall converts nearly all incoming sunlight directly into heat stored in the wall material. The glass panel mounted in front of the dark wall creates a greenhouse effect in the air gap between the glass and the wall surface. Shortwave solar radiation passes through the glass easily and is absorbed by the dark wall behind it. The heat radiated back from the warm wall surface is long-wave infrared radiation, which glass does not transmit. The infrared heat is trapped in the air gap. The air temperature in the gap between the glass and the wall reaches 60 to 80 degrees Celsius on a clear winter day. The second principle is thermal mass storage. A concrete wall 30 centimeters thick stores heat in its mass during the day as it absorbs solar energy. The heat moves through the wall slowly at a rate determined by the thermal conductivity and mass of the wall material. In a correctly designed Trombe wall, the heat absorbed at the exterior surface during the day reaches the interior surface of the wall approximately 6 to 8 hours later. The wall absorbs heat during the day and releases it into the living space during the evening and night, precisely when heating is most needed. The third principle is natural convection. Vents cut at the top and bottom of the wall allow air to circulate between the solar air gap and the room interior without any fan or pump. Cool room air enters through the lower vent, passes through the heated gap, and returns to the room through the upper vent as warm air. The circulation is driven entirely by the temperature difference between the hot gap air and the cooler room air. No electricity, no moving parts, no maintenance. A study published in the journal Solar Energy in 2015 measured the thermal performance of a standard Trombe wall installation on a residential building in central France over a complete winter heating season. The measured heating energy saving compared to an identical building without the system was 68%. The payback period for the installation cost, primarily the glass panel and wall preparation, was calculated at 3 to 4 years at then current energy prices. 68% heating cost reduction, 3 to 4 year payback, 0 operating cost for the life of the building after payback. The study was published in one of the leading peer-reviewed journals in solar energy research. It has never been cited in a home improvement magazine, a building contractor's marketing material, or a home heating system advertisement. Now here is where the story gets very clear. Follow the money. The global home heating industry generates over $100 billion in annual revenue from the sale of heating systems, fuel, and maintenance services. That revenue depends on a single foundational requirement, that homes cannot heat themselves. Every gas furnace sold, every heating. Oil delivery made, every electric heating bill issued depends on homeowners believing that external energy input is the only way to maintain comfortable indoor temperatures in winter. A passive solar heating system built into a home's south wall at a material cost of under $50 that reduces heating bills by 60 to 70% permanently challenges that foundational requirement directly. Consider the scale of what is at stake. The average American household spends between $800 and $2,000 per year on home heating, depending on climate, home size, and fuel type. A 68% reduction in that cost saves between $550 and $1,400 per year. Over a 30-year period, the typical lifespan of a home heating system, that represents between $16,000 and $42,000 in fuel costs that are never paid per household. Multiply that across the 140 million households in the United States, and the number becomes so large that it explains very clearly why the home building industry, the heating system manufacturers, and the energy companies have maintained a collective commercial silence on Trombe wall technology for over 50 years since Felix Trombe published his results. Building contractors do not install Trombe walls. because building contractors have commercial relationships with heating system suppliers and HVAC installers who provide referrals and wholesale pricing agreements. Recommending a passive solar wall that eliminates the need for a $20,000 HVAC system is not commercially rational from a contractor's perspective, regardless of its benefit to the homeowner. Architects do not specify Trombe walls in standard residential designs because residential architecture is driven by developer economics and development timelines, not long-term operating cost optimization for the eventual homeowner. The developer who builds the home does not pay the heating bills. The buyer who pays the heating bills did not design the home. This disconnect is not accidental. It is structural. You cannot patent sunlight. You cannot charge a monthly fee for a south-facing wall. You cannot sell replacement parts for black paint. You cannot build a service contract around a sheet of glass mounted in front of masonry. The entire commercial logic of the heating industry is incompatible with a technology that costs $50 to install and nothing to operate for the life of the building. So the technology exists in academic journals, in passive house design communities, in the work of sustainability architects operating at the margins of the mainstream construction industry. It waits for homeowners willing to look past the products they are being sold and ask what the physics makes possible for free. Here is where the story becomes very practical. Trombe wall technology never disappeared from the communities that prioritize building performance over commercial relationships. The passive house movement, a building design standard developed in Germany in the early 1990s that specifies construction methods achieving 90% heating energy reduction, routinely incorporates thermal mass and passive solar heating principles directly derived from Trombe's work. The Passive House Institute, based in Darmstadt, Germany, has certified over 60,000 buildings worldwide built to this standard. Every one of them heats itself primarily through passive solar principles. None of them requires a conventional heating system for the majority of their heating. Load. The standard is well documented, scientifically validated, and commercially available. It represents less than 1% of new residential construction in the United States. The U.S. Department of Energy's Office of Energy Efficiency and Renewable Energy publishes technical guidance on Trombe wall design on its official website. The guidance includes construction specifications, performance calculations, and regional climate suitability maps. It has been publicly available for years. It is not featured in any home improvement retail environment. A homeowner in Colorado built a retrofit Trombe wall on the south face of his 1970s ranch house in 2017 using materials sourced from a local building supply store. Total material cost, $47 for paint, glass panel mounting hardware, and vent covers. His documented heating gas consumption in the 2 winters following the installation dropped by 58% compared to the 2 winters before. His annual heating bill reduction, approximately $640. His total investment recovered in under 2 months of heating season. The physics works exactly as Felix Trombe measured in 1967. It works in Colorado, it works in France, it works anywhere the winter sun rises on a south-facing wall. Here is exactly what to do, and you can begin this weekend with materials from any hardware store. What you need: black exterior masonry paint, $15-25 per can, covers approximately 10 square meters. Polycarbonate or glass panel, 6 or 10 mm thickness, approximately $20-40 per square meter. Simple mounting brackets to hold the glass panel, $8 12 cm from the wall surface, $5-10. Vent covers for top and bottom vents, $3-5. A drill for vent holes. Total material cost, $40 $80 for a 2x2 meter wall section, enough to make a measurable difference in a standard room. Choosing your wall. The wall must face as close to true south as possible. In the Northern Hemisphere, true south receives the maximum winter sunlight. An angular deviation of up to 30 degrees east or west of true south reduces performance, but remains effective. The wall must receive unobstructed direct sunlight for at least 4 hours during the shortest winter days. Shade from trees, neighboring buildings, or roof overhangs during winter hours significantly reduces performance. Step 1. Prepare and paint the wall. Clean the exterior wall surface completely. Remove any loose paint, dirt, or moisture. Apply 2 coats of flat black exterior masonry paint to the entire wall section you're working with. Flat black absorbs significantly more solar radiation than gloss black. Use flat finish specifically. Allow to dry completely between coats and after the final coat before proceeding. Step 2. Cut the vents. Cut 2 rectangular vent openings through the wall, one near the bottom of the wall section at approximately 30 centimeters from floor level, and one near the top at approximately 30 centimeters from ceiling level. Each vent should be approximately 10 centimeters tall and 20 centimeters wide. These vents allow air circulation between the solar gap and the room interior. Install simple vent covers that can be closed at night to prevent reverse convection. Cool night air sinking back into the room through the system when the sun is not heating the gap. Step 3. Mount the glass panel. Mount your glass or polycarbonate panel in front of the painted wall using the brackets, maintaining a gap of 8 to 12 centimeters between the glass inner surface and the wall. This gap is the solar air channel where heated air accumulates and circulates. Seal the top and sides of the gap with weatherproof tape or foam strips to prevent heat loss from the sides while leaving the vent openings clear for circulation. Step 4. Close the vents at night. Each evening after sunset, close the vent. Covers. This prevents the convection loop from reversing direction as the gap cools. A reverse loop would draw warm room air into the cooling gap and reduce the thermal benefit of the wall's stored heat. Open the vents again each morning when sunlight begins striking the glass. Monitoring results. Track your room temperature at a consistent time each evening for 2 weeks before and 2 weeks after installation. Track your heating system runtime or fuel consumption on a weekly basis. Most installations in appropriate climates show measurable temperature differences within the first clear sunny day of operation. For maximum performance over an entire heating season, clean the glass panel exterior monthly to maintain solar transmission. Dust and pollen accumulation on the glass surface can reduce solar gain by 15 to 20% over the course of a winter. The Roman architect who oriented the bathhouse walls at Ostia toward the winter sun in 100 AD understood something simple and permanent. The sun rises every day, and it brings free heat with it. The engineering question is only how to collect that heat and hold it until you need it. Edward Morse understood it when he filed his patent in 1881 and watched the air behind his. Glass panel heat to temperatures that no fuel cost could have achieved more cheaply. Felix Trombe understood it when his instruments confirmed 68% heating cost reductions in a building that required no fuel to achieve them. The passive house architects in Germany who designed buildings that heat themselves to comfortable temperatures through Scandinavian winters without conventional heating systems understand it today. The U.S. Department of Energy understands it. The physics has never been in question. $100 billion in annual heating industry revenue depends on homeowners not understanding it. Depends on the belief that warmth in winter is a product that must be purchased monthly, that requires a contract with a utility company that cannot exist without a fuel delivery or an electric meter running in the background of every cold day of every year of a family's life in their home. It is not a fuel problem. It never was. It is an architecture problem. And architecture solved it 2,000 years ago with a south-facing wall and the understanding that sunlight arrives every morning at no charge. The south wall of your home is there right now. The winter sun is rising on it every morning. The black paint is at the hardware store. The knowledge is here. Subscribe and share this video. Every share reaches a homeowner who will spend less on heating this winter and every winter after it. Every subscription keeps this channel opening the vaults the energy industry thought were sealed forever. The next vault opens soon, and what is inside will change how you look at the water falling on your roof right now, and the $0 collection system that provides hundreds of gallons of free water every month that the water utility industry has worked for decades to make you believe requires their infrastructure to exist.